Hi, so in this video, I just wanted to walk through some equilibrium problems involving ionic compounds that have ions that come from weak acids or weak bases, right, and kind of see how we can work through those. So to get us started, let's look at this example where I have a solution of sodium acetate. Now, acetate is the conjugate base of acetic acid. Acetic acid is like the acid found in vinegar. It's a weak acid, right? It's not in our list of strong acids. And more importantly here, we're given the acid dissociation constant of acetic acid as 1.8 times 10 to the minus 5. Now I want us to find the pH of not an acetic acid solution, but instead a sodium acetate solution. We're given here its molarity as 0.0450 molar. And so to determine its pH, right, I'm going to want to think through what exactly my solution at hand is going to do. Again, I know that I have a Ka given for acetic acid, but the solution that I'm looking at is not acetic acid, right? It's instead the conjugate base of it. So like any conjugate base, what it's going to do is act like a base would, right? This sodium acetate, or really just the acetate within it, is going to react with water to form hydroxide and its conjugate acid again. Even if I don't know the full chemical formula of acetate or acetic acid, right, I know that it's some kind of anion for acetate, so I just put in here as a little placeholder A minus as my acetate, and then HA as the acetic acid. And so I've set up my ice table like so, right? I have my initial concentration of the A minus as 0.0450, and then the final concentration is again 0.0450. The concentrations of OH minus and HA, those are both going to be equal to X. Now to actually solve for X here, right, I'm going to want to not just use the Ka that's given because this isn't an acid dissociation equilibria. Instead, I need to solve for the Kb first, right? So as we saw previously, the Kb of a weak base or the conjugate base of a weak acid is related to the Ka of the acid by Kw, or the autoionization constant of water. Specifically, I can calculate Kb as Kw divided by Ka, so that Kw is a constant, 10 to the minus 14. Ka we're given, and so we can solve then that Kb here for this reaction is about 5.6 times 10 to the minus 10. I can use that then to solve for X, right, setting up my usual products over reactants expression, and I find that X is equal to 5.0 times 10 to the minus 6. This X, again, if we look back at our ice table, is the concentration of hydroxide at equilibrium. So with that, I can find, say, the pOH of the solution, right, as the minus log of 5.0 times 10 to the minus 6. So pOH equals 5.3. That means then that pH is equal to 14 minus that, or 8.70. All right, but so this is an example of a salt that is made up of the cation of a strong base and the anion of a weak acid, right? Sodium corresponds to like sodium hydroxide, one of our strong bases. That sodium in there doesn't do anything in the reaction, right? It basically just acts as a spectator ion. But the acetate, on the other hand, right, that has the ability to act as a weak base, as we see right here. And so that gives us then an overall basic solution in the end. That's why we have this pH higher than 7 here. Let's look at another example of a salt. So here I have a solution of sodium carbonate. Again, sodium is just going to go off, float around as a little spectator ion. The carbonate, however, relates to carbonic acid, or H2CO3. Now, carbonate, you should know from your list of like common polyatomic ions, this is CO3 2-. Again, the CO3 part is maybe not so important, but what is really important is that it has a 2- charge to it. As such, carbonic acid, you can see, has 2 Ka constants, right? Meaning that when you take carbonate and you have 2 protons on there, right, each of those protons has its own Ka associated with it. All right, but so again, if I want to find the pH of a, let's say, 1.00 molar solution of sodium carbonate, because this carbonate is the anion, right, it's going to act as a base. So again, I have my base ionization equilibria set up right here. And although carbonate itself has a 2- charge, when it reacts with water, it's only going to take one proton at a time. So our products here are OH minus, as usual, the hydroxide, but then also HA minus, right? Only one additional proton added onto that carbonate. Again, I have like my initial and equilibrium amounts kind of set up through the ice table. And again, I'm going to want to determine the Kb of this reaction because it's a base dissociation using the Ka. But the question here is, which Ka do I use? Right, so you can see from our description that we have Ka1, we have Ka2, which Ka is going to correspond to this Kb. What will help is if we think back to what the actual chemical equations look like for these sequential Ka values. So again, anytime we have like a polyprotic acid, they're going to have multiple steps, so multiple protons. The way that the equilibria look relative to these like Ka1, Ka2 is like so. So the first proton leaving, that corresponds to Ka1. So if we have, say, a diprotic acid, like carbonic acid, starts off as H2A, and then it loses one proton to produce HA minus. That corresponds with Ka1. Following that, we can then take the HA minus and remove another proton, giving us a 2 minus. Because that's the second proton leaving, that corresponds with Ka2. Now what I want you to do is look at the base dissociation reaction that we have in our ice table and compare it to these two equilibria that are shown right here. You'll notice that between these two equilibria, right, the one that kind of most closely matches the one that's in our ice table is Ka2, right? Ka2 has HA in it, Ka1 also has HA in it, but in Ka2 there's also the A2 minus, right? That's not featured at all in the first equilibrium constant, and so that really affirms to me then that Ka2 is the Ka of interest here. So when I calculate my Kb value for this ice table and this reaction that I have drawn out, right, I'm going to use Kw divided by Ka2 to do so. And what I find then is that the Kb associated with this reaction is about 2.1 times 10 to the minus 4. And again, I can use that to now solve for X in my ice table, just kind of setting things up as the products over reactants. I find X equal to 0.015 molar. Again, because this is a base dissociation, that X is the hydroxide amount, so the minus log of that, or the POH, is 1.84. And that means then that the pH is equal to about 12.16. All right, so again, this one's a little bit more tricky because it does involve a polyprotic acid, or really the conjugate base of a polyprotic acid. But I find it really helpful to think through, what the different Kas represent as an equilibrium, to trace that back to, which Kb or which Ka you want to use to find your Kb. As one last example right here, I have also a question on sodium bicarbonate. Now, sodium bicarbonate is Na plus for the sodium, and then the bicarbonate is the HCO3 minus. So basically that HA minus from our previous example. Now, if we want to find the pH of 1.00 molar sodium bicarbonate, we again have like Ka1, Ka2, but in terms of actually solving for this, it's actually really, really difficult because there are kind of these like dueling ways that the bicarbonate can go, right? Bicarbonate is itself an amphiprotic substance, meaning that it can either donate a proton or it can accept a proton. The fact that that bicarbonate can go either Ka or Kb, right, makes it a little messy. I do have a link here in my slides that connects to kind of like how you can work out the math for a sodium bicarbonate example, but it's really messy. It's very difficult, and it's not something that we'll really consider. So instead, we'll stay away from amphiprotic substances or salts that include, say, like a bicarbonate or like a hydrogen sulfate or something like that. And we'll focus on just like purely deprotonated substances, or say, for instance, like the cations of like a weak base, right? That will be maybe included, but nothing quite as complicated as this. All right, but so please let me know if you have any questions on that, and I'm always happy to help. Bye.